Hey everyone, and welcome back to another episode of the QRL Show, the place where you come for the crypto and stay for the quantum. In today's episode, myself and Michael Strike are joined by the team at Geometry Labs, Brandon Goodell and Mitchell Kravitz there. Guys, it's good to have you with us.
Thanks for having us.
Thanks for having us back.
Yeah, well, with funding from the QRL Foundation's grant program, Geometry Labs, have developed highly aggregatable post-quantum fusion digital signatures for the QRL ecosystem. And for those of you that are either watching or viewing this, that might seem like a lot, but really our intention with this episode is to help unpack fusion signatures and talk about the exciting work that Geometry Labs is doing. So we're going to, as we cover a solid variety of questions through this episode on what fusion signatures are to practical applications, and maybe jump into like parameterization and maybe even ethical and societal implications. We're also going to have a Reddit AMA that's following this episode. So if you're watching this, you can see the link to that in the show notes if you have a question now or later. And we'll drop the link to that there. So now that that's covered, I think as a first initial question that would be good for you guys is starting out, could you guys give us a quick 1 or 2 minute background on what Geometry Labs is about, and within that, what the relationship working wise is with QRL, and then we can jump right into fusion signature questions. Brandon or Mitchell, whoever wants to take the first one.
So Geometry Labs is a cryptography R&D company. We focus on building tech for post-quantum, quantum secure distributed systems. We execute R&D often at like the algorithm development, theory, and prototype level. So various aspects of our works have ranged from parameterization to security proofs to design to prototyping. You may remember, I think in past shows, we've discussed work for the QRL ecosystem in terms of adapter signatures and secure fountain architecture, which was quantum secure storage level improvements. And now we're talking about fusion signatures. And all of this has been made possible by generous grants from the QRL Foundation.
Jumping right in from that, since the subject at hand today is on fusion signatures, let's jump right into that question for those watching, viewing this. What are fusion signatures? That's going to lead into kind of all our other questions today.
Right. So fusion signatures are a one-time signature scheme that are lattice-based that the QRL ecosystem has, I shouldn't say the QRL ecosystem has expressed interest in replacing the XMSS signatures, but they're always interested in expanding and looking at what's out there as possibilities. And one of the hard things to deal with XMSS signatures is they don't really aggregate or batch very well. And so as a consequence, 1,000 signatures is 1,000 signatures. So in the course of trying to look for scaling solutions, the QRL Foundation contacted us, and they wanted us to look into different ways to scale authentication in a way that's quantum secure. And fusion signatures do this. So they are one-time signatures that aggregate. So this allows us to basically, I don't want to say stack, but it's more like add, like literally multiple, like on an arithmetic level, add signatures together, so that you can just post a sum of signatures on a message board, and people can still verify that all the corresponding messages and keys were used to construct the signature. So this way, to put it another way, it's sort of like a zipping 1,000 signatures together into a single small signature that can still just be verified as a zipped signature. So signature aggregation is an extremely useful thing for scaling solutions for blockchains. When you start talking about large scale key management, what happens at Amazon, you have to have thousands of authentications a minute or per query. I shouldn't put a unit of time on it. And so anything where you can combine everything down and then just get a logarithmically sized object to represent 1,000 things is really, really, really fantastic. And that's exactly what the fusion signatures do.
And just to help the listeners or viewers picture kind of mechanically what this looks like or what the process is, a regular non-fusion one-time signature process looks like, one, I generate a secret key and a public key, a verification key, and then two, I sign a message, and then you can share that signature. And then 3, someone else can take the message, the signature, and the verification key and make sure everything checks out, hasn't been tampered with. What Fusion Signatures adds is actually a step between generating the signatures and verification, where optionally it's this adding step that Brandon described can be carried out non-interactively, even by a non-participant. So one of the really cool things here that I think has implications when you're looking at proof of stake and other distributed systems applications is that we don't need like some designated special party that is going to be managing aggregation for an epoch or something, right? It's all non-interactive, all can be done by anybody on the fly.
Permissionless.
Are there any potential applications of Fusion signatures outside of the QRL ecosystem? I think this would be a nice one to cover.
Yeah. So the first thing that comes to mind is just general authentication. So every time you go to a website and it has HTTPS in front of it instead of HTTP, there's handshakes and signatures being checked behind the scenes. This ensures that no middleman can get between you and Gmail and make sure that like you're actually interacting with Gmail. Or whatever service it is that you're using. Uh, yeah. Unfortunately, all that authentication is, as people who listen to this podcast are more than aware of, all that authentication is based generally on pre-quantum encryption or signatures, and so pre-quantum cryptography. Um, so, in order for things like Amazon transactions to be secure in the future, even visiting a website securely, eventually you're going to need some sort of post quantum authentication going on. And this is one step towards that. Uh, the fact that things get aggregated together, it suggests certain use cases, right? So, like the financial world, where you have a lot of or authentications happening at once whenever transactions occur, this is a good case, good use case for aggregating signatures. And like I said earlier, Amazon key management, like they have to deal with a very large number of queries a day, and they have to authenticate with for each query some signature someplace. So anytime that you can smash things together, it's really really powerful. So the potential applications of fusion signatures go well beyond the QRL ecosystem.
So that sounds interesting, guys. I have a question on some of that. So, Brandon, you were talking about HTTPS and TLS. A lot of this sounds like it ties in. Could be one of the use cases. Might be post quantum secure Web3, being able to encapsulate some of those being able to encapsulate the HTTPS, the legacy HTTPS and TLS, and encapsulate that into Fusion signatures and signing that, and just keep, in order to support legacy protocols, just wrap it around. Is that possible?
So this may not be true from like a pedantic cryptography proof perspective. This is just kind of me talking colloquially. There's some cases where if you add together 2 crypto systems and one breaks, you're in worse shape, right? So let's say I have a secret message that I'm sending, and I encrypt it with encryption algorithm A, and I mark it down, and then encrypt it with B, and mark it down, and I just stick those together and send them both. Well, if either gets broken, the message is out, right? However, with digital signatures, if I have a message and I sign it once with whatever classic one, and then I sign it again and I give you both signatures, if one of the signature schemes gets broken, the other one should still be okay. So I think that kind of coupling actually maybe.
So there is a risk here. The more general problem in the crypto world that we're talking about, which actually is like the more interesting thing, is the abstractification of things for me, is called universal composability. And so if you have 2 crypto protocols that are secure, and you follow a protocol where you do one then the other, and you compose them together, like composing functions f of g of x or whatever. Um, uh, it, it takes quite a bit of intellectual framework to prove that composing 2 secure systems together ends up being a secure system, unless it's really really obviously secure. So I would say that there'd be a big danger in general in just like, for example, signing an old legacy thing using one-time signature scheme. You can only use those keys once. I don't know. There's a lot of failure of imagination attacks, so to speak, where it's just like, just because I can't think of an attack doesn't mean an attack doesn't exist. So I would say it'd have to be like the details would have to be nailed down real carefully, and then but in principle, the idea is that there should be some way to safely migrate from the legacy HTTPS system and TLS system to something that's quantum secure.
So that's always the crux, right? Is moving forward but maintaining backward compatibility. And to Mitchell's, to your point, not building in the more dependencies you build in order to maintain that backward compatibility, the more likely something is to fail. And if you have 1 week in those transactions with HTTPS, TLS, XMSS, or Fusion in this case, any one of those fails, to your point, yeah, I mean you lose everything. Brandon, for you mentioned one-time signatures. So as far as Fusion signatures goes, since Genesis, as our community knows and many of us know, we currently use an XMSS NIST recommended hash-based signature scheme. Fusion, from what it sounds like, is replacing many of those functions. So in the context, the question I have is in the context of OTSs, XMSS, and Merkle trees, which parts of those does Fusion forklift out and replace, respective to, I would say, just those three things?
It's hard to compare one-time signature schemes to many-time signature schemes. And my understanding is that the XMSS scheme uses a tree-based approach to handle keys so that you can sign many messages with the same key. But not necessarily an infinite number of messages, if I recall correctly. So it's sort of like a weird comparison to compare it directly. But if you were going to design a transaction protocol around Fusion signatures that, say, also accepts legacy XMSS stuff, right? So that you could transition over to this new transaction system. And let's call that QRL2, even though this is a fantastical thing. I'm not proposing that this exists or that anybody's planning on making it. But if you had some transaction system that was going to be based on Fusion, you would have everything that occurs in that system would be based on some signature, right? So every single time a transaction occurs, you have to sign with a key, and every time that a staker agrees that a block is valid, they need to produce a signature, and so on and so forth. So all of these would have to be signatures that come from this one-time signature scheme, which means all of those keys need to come from somewhere, right? They can't just be random keys. They have to be linked to like previous transactions or some stake lottery or something along those lines. But once all of those keys are determined through transactions or staking or however those keys are determined, all of these signatures can just be added together and smushed down into a single signature. So if I have 1,000 transactions in a block, each of them spending a single key, then I have 1,000 signatures. And then if I have a single staker that has signed the whole block, that's one signature. And I can combine those 1,001 signatures down into a single aggregated signature that could be checked for the entire thing. And then as soon as you check it, you know at least the authentication has occurred. You then need to check other things like fees and balances add up to zero and stuff like that. So your question is this is like, what is being forklifted out? And it's every single time that an authentication occurs on the QRL network would be replaced with one of these signatures, so that every time that these signatures are being written to the blockchain, you may as well just aggregate them all down, and you only write down the zipped signature. So as a consequence, the three things that you asked about were XMSS, one-time signatures, and Merkle trees. No Merkle trees need to be handled. I mean, you might. So this is actually something that I think about a lot, because how do you handle all of these one-time keys that are being generated for this signature scheme? In the end, you're going to want some like tree-based approach locally, at least, handling all of the keys that you have, and you probably are going to store them in a Merkle tree someplace. But the verification of where you placed it in the Merkle tree has nothing to do anymore with whether or not the transaction is valid or whether or not your key has been used or anything along those lines. Fusion signatures are a one-time signature scheme. It would be sort of like, if you're asking kind of like the George R.R. Martin, like Game of Thrones fantasy version of what QRL could be, right? You're talking about like replacing all the every single signature that occurs anywhere on the network. Replace it with one of these signatures so that you can aggregate them down. But you only need to really worry about the ones that get written to the blockchain. I think I answered your question.
And another way to kind of look at something similar, if you zoom out and instead of saying which pieces of the cryptography, but rather which pieces of the protocol would fusion signatures be potentially helpful for, you can look at it both in terms of the transaction piece, which Brandon kind of covered a lot, and being able to use fusion signatures to produce and compress those, or not compress, combine those, aggregate them. But the other big thing is proof of stake, right? Where we have a proposed block template. We have a large number of validators. We want all of these validators to say, yes, this is the one I'm signing off on and approving. And then the nice thing is, if you're using that for your validators, then you can just in your block header have a single like aggregated proof. And this is all 1,000 validator or aggregated signature. And it's all 1,000 validators signed off on them. You need the verification keys too, but you can at least tighten up a lot of that. So and even though we usually talk about them separately, using it for transactions or potentially using it for proof of stake, there's even theoretically, and this may not be practically desirable, but theoretically, you could even aggregate some of your stake signatures with your transaction signatures, I think.
Yeah, like an ideal thing would be one signature per block, like one aggregated signature per block that covers all of the transactions inside and all of the stakers. And what's really, really cool, in my opinion, the coolest thing about all of this is that now the limiting factor is how many keys the verifying computer can fit in its RAM, because you end up having to hash all of them together, right? But like, if you can fit 32,000 keys in your RAM, I can give you a scheme that has 32,000 aggregation capacity, right? So in theory, there's really no reason to have more than one signature per block, which I think is just wild.
Yeah, for the next question, let's touch on one related to security. How does the bit-hardness serve as a proxy for security estimation in Fusion, and what is the estimated post-quantum security level? I think that'd be a good one to cover, Brandon.
Okay, so let me talk about bit-hardness first. If something takes time t and has probability epsilon of success, then the logarithm of t over epsilon is the bit-hardness of that thing. So if it takes a year and you have a probability of 10%, you do 1 year divided by 10%, and you take the logarithm of that, and that's your bit-hardness. Of course, the units are a question, right? Because how do you compare a year to percentages? That we're going to leave that alone for right now. The reason that bit-hardness is interesting is because this way, if I'm like, all right, my bit-hardness is 128, it might take some unit of time t and some probability epsilon of success. But if you work this out, if it takes like 1 unit of time and your bit-hardness is 128, that means that your probability of success is 2 to the negative 128. So that means that something with a bit-hardness of something like 128 is either very, very, very unlikely to succeed, or it's very likely to take a very long time to succeed. So it like sort of combines the time it takes to do something and the probability of success. And 2 to the negative 128, I hope that your viewers are familiar enough with math to know that 2 to the negative 128 is a really damn small number. It is so small that like 2 to the negative 120-ish is roughly the known number of particles in the observable universe, right? We can only see out so far before we can't see any further. And if you take the volume of that known observable universe and you count every single fundamental particle, I don't mean atoms, I don't mean electrons, protons, I mean like fundamental particles that build up to be electrons. You count all those up, you get something like 2 to the 100, which means if you have something that has a bit hardness of 128 bits, then you would have to take the entire known observable universe, turn it into a computer, the entire thing, and you still would have a hard time solving that problem in a reasonable period of time. So 2 to the negative 128 is small. 128 bits of security is strong. So that's how bit hardness like serves as a measurement of security. Bit hardness, though, is sort of like hard to measure because I mentioned time and units and stuff like that, right? So sometimes it's measured in the number of operations that the computer has to run. Sometimes it's measured in literal units of time, like seconds or years or something like that. And NIST, or NIST, National Institute for Standards and Technology, for their latest post-quantum algorithms, they, instead of defining specific bit hardness levels of their algorithms, they had 5 different security levels, which correspond to how hard it is to break known algorithms. And of course, the hardness of those algorithms were all based on the difficulty it would take in terms of units of time. So in the end, it all works out to be about the same. It's like a bit hardness thing. And Fusion has been parameterized to be 128-bit secure at least. But actually, we were really, really aggressive in the way that we parameterized it. And this comes up to our next question. This has to do with something that NIST calls the core SVP metric. So when you're solving a lattice problem, you want to know how hard the problem is in terms of bit hardness. So what you do is you throw the best known algorithm at it, which is known as the shortest vector problem, or excuse me, which is known as the BKZ algorithm. And unfortunately, I forget the names BK and Z that led to that name. But the BKZ algorithm solves the shortest vector problem. It finds the shortest vector in a lattice. And NIST wants normally the way that you would solve a lattice problem is you would traverse the lattice and you would call an oracle to solve the SVP problem for some amount of data that you collected from that lattice. And you would get back a shortest vector. And then you would do it again and again and again and again. And then hopefully eventually you'll find something that's short enough to be considered a secret key. And that breaks the lattice. But one way to assess the bit hardness would be to count how many times you need to do that trick in total and set the hardness based on that. Except these algorithms tend to perform very, very well after only a few short moves. So that's not actually a very, very good metric. If I think it takes 1,000 times, but you can really run it and be done in 8 steps, then that's not so good. So the way that NIST set this up, they set this up so that we use the core SVP metric to assess security levels for post-quantum security in lattice schemes. And that is basically counting only one SVP call. So we're really, really conservative and aggressive when we say we think that this is going to take 128 bits of security. That means if the most powerful adversary in the world built the entire universe into a computer, they would still, and they had to make only one call to this oracle to solve the problem. It would still take them longer than the age of the universe to do it. So I believe now, finally, I answered your question.
Moving to the next one, how do the narrow tightness gaps in Fusion's proofs enable more efficient parameters compared to other types of schemes?
Right. So the short version of this is actually not very mathy at all. Actually, this is a real punchy one. A tightness gap is when I try to solve problem A with another problem solver B that does something else. If it takes an additional amount of time or it reduces my probability of success or whatever, that introduces this tightness gap. And you have to take that into account when you assess bit hardness. Because our proofs for the Fusion signature algorithm are more efficient than the other, and like, I don't want to use the word elegant because that has this like judgy word to it for our proofs. Our security proofs skipped steps, like removed, or they're just more efficient than the ones that were originally written for the Fusion, for the original signature scheme. So as a consequence, we were able to make our parameters significantly smaller. So all of our keys and our signatures are significantly smaller, and our aggregation capacity is larger. That's the long and short of it.
A good question I want to cover is on limitations and challenges. So, what are some of the challenges or limitations in the implementation and adoption of fusion signatures, and how can each of these be addressed?
Sure. The main limitations and challenges that we've had so far in programming Fusion and in just programming in general for lattice-based stuff, it has to do with like the number theoretic transform and handling the arithmetic that underlies all of this. So the number theoretic transform is like the fast Fourier transform. So anybody who was unlucky enough to take a fast Fourier transform class or an electrical engineering class in college, they remember some stuff about it. But the thing is that you can multiply polynomials very quickly with it. And it's a really, really famous and well-known algorithm that's been around for a very long time. And the number theoretic transform version of it is sort of like a discretized version of it. That's even more discrete than the discrete Fourier transform. So the main challenges that we've had so far have actually just been making sure that our implementations of those things work appropriately. There are already a bunch of implementations out there for these things, but we wanted to make sure that we weren't relying on any external libraries, and we just kept running into problem after problem after problem. But the stars aligned, and over the past couple of weeks, some real great magic has occurred.
The fast Fourier transforms the conventional equivalent of the quantum Fourier transform.
I actually don't know much about the quantum Fourier transform, but yes, that's correct.
I was making sure. I wanted to make sure what I was saying makes sense in the past.
Yeah, the Fourier transforms. Yeah. That's the interesting thing. It is absolutely wild how much that transform appears in like pure graduate level mathematics. Like it seems like such a weird like one-time thing the first couple of times you learn about it, and then it turns out it's just like everywhere, man.
The next question I want to cover is, what are some practical applications of fusion signatures, and how do they enable large-scale POS consensus and MFN multi-sig wallets and mechanisms for on-chain governance? Mitchell, if you could cover these in order, however you want, this would be great to cover.
Yeah. So basically, all of these different use cases kind of boil down to MFN authentication. Theme for today's show, authentication. So in large scale proof of stake, you're looking for validators to authenticate their identity and that they approve a block. For multi-signature wallets, it's you're authenticating your identity and approving a transaction. For on-chain governance, it's authenticating your identity and voting or anything like that. And so I think it's good to have like efficient tech that covers all of these use cases, right? And even if like QRL doesn't have on-chain governance now, it's nice to have these options in the future. I actually think it's potentially especially important in the case of on-chain governance for like enabling democracy, in the sense that efficiency is important here, right? If it costs $25 to place a vote, or it costs 2.5 cents to place a vote, that's going to make a huge difference in who can participate, the egalitarian nature of the voting, all of that. So yeah, that's kind of in a nutshell how it kind of all ties together.
Yeah, so just to clarify real quick, for M-event authentication, a lot of people confuse that with threshold authentication, which threshold schemes in cryptography are very, very specifically designed and defined, so that, for example, you don't necessarily even know that a threshold signed it. And you can't really tell the difference between that and a regular old signature or whatever. With aggregate signatures, you can easily check whether the aggregated signatures are all on the same message and whether or not you have more than M of them, right? So you can do M of N authentication. It just technically doesn't fit the definition of thresholdizing. So there's a lot of threshold-based functionality that is also capable, or that you can also achieve with aggregate signatures that technically aren't thresholds. So I just wanted to clarify that really quick, just for the pedantic people in the audience.
So on aggregatable, aggregatable signatures, I think we've talked about this in casual conversation, but for our viewers, when the signatures are aggregated, are they loss decompressed in any way as they're written immutably to the chain? Can they be read playback from the beginning, or does that playback not actually exist and it's written based on the consensus of the nodes at the time, all agree, and then you move on, and the immutability itself actually obscures the addresses of those transactions. How exactly does that work when you aggregate everything together? I think that would be good for our community.
Right. Since all of the keys are public and you need those for verification, there actually isn't much privacy or obfuscation in that way. As far as playback goes, I would interpret that as like going from the aggregate signature to the original signatures. There's no way to do that. I would in fact think of the signatures in this scheme as ephemeral signatures, and the aggregate signatures as the regular old signatures. It just happens that the aggregate signatures can also verify multiple messages and multiple keys.
So that's an interesting, possibly important distinction based, for example, how Bitcoin would work, where okay, for pay to public key transactions, not necessarily pay to public key hash transactions, because that's much more difficult to. You can still play it forward, but it's difficult to play backwards, right? On pay to public key hash because of the one way cryptographic hash function. So, okay, sounds good. Thank you.
Yeah.
Yeah, coming out of this question, I want to touch a little bit on ethical and societal impacts. So, are there any societal or ethical implications of using signatures, and how do they fit into the ideology of blockchain compared to other signatures? However, you guys want to compare and contrast this. This would be cool to cover.
I could talk for hours on this, man. Okay, so do you guys know Jevons paradox? Let me make sure that I have this right before I say it out loud. Yeah. So Jevons paradox basically says if you build a bigger highway, more people get on the highway. Or if you increase electrical efficiency of light bulbs, then people just leave more light bulbs on in their house, and the total load to the system doesn't really change. So there's this ethical question about whether or not scaling blockchains up actually does anything, or is it just natural for the system to occupy the space that it can occupy, and whether or not scaling up actually makes things worse because what you're doing is increasing the efficiency of the system and therefore increasing the throughput of the system, therefore increasing the demand of the system, therefore increasing the footprint of the system.
Wouldn't the new use cases in that scenario, wouldn't the new use cases have a measurable value add? For example, like when you say that, I'm thinking the first thing that comes to my mind is hard drive tech. We can build a bigger hard drive. It's just going to get used. In that in that in that leap forward, I almost said quantum leap forward. In that leap forward, there's value add theoretically that I don't think is non-zero, but we're not going to give you more power. You're just going to waste it.
Well, I mean, we live longer lives now, and what do we do with it? We just sit at desks. So actually, that reminds me of this character from Catch. This reminds me of this character from Catch 22, who tries to cultivate boredom to make his life last longer, so that he lives longer. Because time seems to move slower when he's bored. So if he wants to live as long as possible, that means he should be bored the whole time. So he's like sitting around, living no life whatsoever for as long as possible.
I'm always of kind of the like cypherpunk mindset that access to cryptography should kind of be like a fundamental human right in this day and age. You know, 1,000 years ago, you could use a wax stamp to authenticate a letter, right? But at some point, that became not secure. And so we invented, digital signatures that we've been using. Well, at some point, those might not become secure. And I believe that at any point, like I should be able to send a message to Brandon, and Brandon should be able to know, is it actually the message I sent? And I can't use a wax stamp. And if quantum computers are around, cryptographically relevant quantum computers are around, I can't use just like today's vanilla signatures. And so I think personally, maybe this is a little grandiose, but I think it's actually really important to make sure that people moving forward have these tools, availability to open source algorithms, and tooling to make sure that they can trust their communication.
One last question before we kind of wrap things up with this episode is, could you briefly cover efficiency? I'd love for you to talk on what's the efficiency for fusion signatures. If you could expand on this for us, Brandon, this would be great.
Yeah, absolutely. One of the things that I'm most proud of is how efficient we got things. But the short answer is it's not more efficient than Crystal's dilithium or Falcon, if you count just one signature and one key. The thing is, for a one-time signature scheme, you have one signature, one key, right? But to compare against the many-time signature scheme, well, somebody just needs to post a key once over there, and then they can post multiple signatures. So the cost of the key in terms of post space goes down over time. And it's like really not that people tend to discount the size of the key because it's going to be only posted once. But for the one-time signature scheme, you have to count the keys and the signatures together, which makes beating crystals, dilithium, and falcon a little bit difficult because you're counting all of your keys and your signatures together, but we were still able to come up with parameters that do it. So we actually parameterized 3 separate parameter sets, fusion light, mid, and heavy, based on these. And for the light scheme, the keys are 496 bytes. They're 0.496 bytes, or 0.496 kilobytes. Which is really, really nice and small. The signatures, however, which are like ephemeral signatures, remember, those are almost 22 kilobytes, which is actually really, really rather large. But they aggregate down into only like 47 kilobyte aggregate signatures. And those 47 kilobyte aggregate signatures can support up to like 1,796 signatures. So we took something that cost like 22 kilobytes each, and then we smashed 1,796 of them down into something that cost 47 kilobytes. Right? Like that's pretty cool stuff. That's so for Fusion Light, that's something that I only need to aggregate 25 signatures together to be more efficient per signature than crystals, and I only need to aggregate 276 signatures together to be more efficient than Falcon. For the Fusion Heavy scheme, we actually can't beat Falcon. Falcon's too efficient, but we would need 183 signatures to beat Falcon on the Heavy scheme. And in that case, we're talking about like 80 kilobyte signatures. So, and like a 2,800 aggregation capacity. So overall, it's not quite small enough for something like TLS or HTTPS, but it's unless you're like doing an aggregate verification thing. But for something like a large scale key management exercise through like some sort of database, like cloud service or something like that, Fusion is getting real close to it's. I think it's there. It's pretty cool.
As a wrap-up question, where's a good place for people if they're just learning about this topic that we're covering right now in this episode? Maybe they've read the blog a little. Where's a good starting place for them to learn more, so to speak, on fusion signatures and the work that you guys are doing?
I would say just check out at the blog post be a good place to start, and then they're not public yet, but we'll have public open source versions of the algorithms and all of that.
Yeah, wrapping things up, as always, myself and Michael really appreciate always having you guys on to both have a conversation. It's always good, and it's exciting to hear about the progress and work that you guys are doing at Geometry Labs tied in with QRL. For those watching, as we mentioned earlier, we're having a Reddit AMA. So I'm going to drop the link to that in the show notes. If anyone wants to reference, if you have a question, or if it's after the Reddit AMA takes place, you can read questions big and small that get answered following this episode. More than anything, myself and Michael, we appreciate the conversation. And thank you, Brandon and Mitchell, for a great conversation. Thanks, guys.
No problem. Have a good day, guys.
Awesome. Thank you so much.